Hello everyone, my name is Juliano Franz, and in this video I'm going to talk about the work by Reilly, Joseph Malloch, and myself called Compensating for Perspective-Based Distortion on Large Interactive Floor Displays, the SpaceHopper Field Experiment. So these two experiences are ever more embedded in a physical space. Therefore, many of the interaction modalities are also physical. Examples of such experiences include virtual reality, mixed reality, and particularly in this work, large projection surfaces such as floor displays. We found that floor displays are very interesting, especially because they allow our players or users to step into the content and they foster immersion that way. However, they also propose a set of unique challenges. One of these challenges is that users cannot move away from a display, different than a wall display, for example. And because they are always interacting close to the floor display, there is always a problem of perspective-induced skew. That is, objects that are far away from the observer get skewed in shape and size. To address this issue, we create a technique called perspective compensated view. In perspective compensated view, objects are scaled as they move away from the observer, but they are scaled by keeping the constant angular size. That is, from an observer perspective, even though the object is moving away from the observer, the size of the object remains the same. To evaluate perspective compensated view, we created an interactive experience called SpaceHopper. In interactive experiences, we need to track our players. To do so, we had 4 overhead Microsoft Kinects. We project on the floor using 2 stacked short throw projectors to remove shadows, and we have a large display surface of around 30 square meters. SpaceHopper was made to be played at night. It is highly inspired by Atari's game of Asteroids. However, in our implementation of the game, the player does not have the same egocentric view because now the player is immersed in the asteroid field and the player is the spaceship himself. To play the game, to fire and move the ship, the player bounces on a hopper ball. So every time the player bounces to move, he'll be moving himself, that is, he'll be moving the spaceship, and he'll be firing if he wants to. The objectives are similar to the original game. So the first one is to destroy the asteroids. For every large asteroid, it spawns 3 medium ones, and then for each medium, it spawns 2 small ones, and then they're gone. There is also a flying saucer that shows up from time to time and it shoots at the player. And the last objective is to survive the most amount of time as possible. Just like the original game, we increase the frequency in which asteroids and flying saucers spawn over time. We implemented 2 control modes. The first one is similar to the original game that we call bounce to fire. That is, every time the player bounces, it's going to shoot a laser shot, a directional laser shot where the player is currently looking at. The second one we call bounce to repel, which is what we think a more natural way of interacting with a hopper ball on a floor display. Every time the player bounces, when it creates a 360-degree repulsion wave that repels asteroids away, and now once an asteroid hits another one, they get destroyed. Here we can see an example of a player playing the bounce to fire modality. And here we can see an example of a player playing the bounce to repel modality. We created this visualization that looks like a droplet in water. To evaluate perspective compensated view on SpaceHopper, we deployed it as an exhibit in an event called Nocturne at Night in the city of Halifax, Nova Scotia. The event ran from 6 p.m. until midnight. More details about the implementations and design details of SpaceHopper can be found in the paper. So in our field experiment, we had 2 research questions. First one is, can perspective compensated view increase player awareness through egocentric adjustment of game object size? And the second one is, in what ways does control modality, that is, bounce to fire, bounce to repel, interact with the effects of perspective compensated view? We ran a 2x2 between participants study, where one factor was the control mode, fire or repel, and the second one was perspective compensated view, that is, on or off. We recruited participants from the queue, however, participating in the study was now mandatory to play. So, summary of what we observed, we collected 64 participants. Around 60% of our participants had played Asteroids before. We saw a significant difference in score in participants exposed to perspective compensated view in the bounce to fire. So in the bounce to fire, participants had higher scores with perspective compensated view than without. Interesting enough, we did not saw the same with bounce to repel, and we're going to talk about why we think so later on. It's important to also note that in asteroids, if you have a higher score, that usually means that you also survive for longer. We also recorded head rotations, and we evaluated in two different measures. First one is rotation rate. So that means the total head rotation normalized by the time. And it tells us if people were aiming. So lower rotation rates tells us that people were aiming more carefully, and higher tells us that people were firing at will. And the second one is the spectral centroid of azimuth, which tells us about glancing, so quick glancings from one side to the other. And we observe a significant difference where participants exposed to perspective compensated view had lower glancing measures, which tells us that they were more aware of the game field. After a field study, we evaluated perspective compensated view in isolation in a controlled laboratory environment. We had three conditions. The first one is two objects and they're moving towards the player, or in our case, our participant. The second one was four objects grouped together and they were static and they would set at three different distances from the observer. And the last condition was four objects separated, also static, and they would set at three different distances from the center of the floor display. The participant's objective was to choose the smallest of the objects as quickly and as precisely as possible. So here we can see our three conditions. On the left, the two moving objects. On the middle, the four objects separated in what we call the far distance from the center. And on the right, four objects grouped together in what we call the medium distance from the observer. It's important to note that we opt not to use raycast as a selection tool to avoid confounding, and rather you ask for the participant to tell the color of the object they wanted to select. We did screen our participant for color blindness before the study. So from our control study, we collected 12 participants, and via repeated measure, we have 2,880 trials. We observed that in all conditions, participants exposed to perspective compensated views were faster in selecting the object that they want to. To start summarizing this video, we created a window-while study, and we backed our findings in a second control study. Results from both of studies indicate that perspective compensated views can facilitate users to disambiguate between different distal objects. Regarding the difference in scores in bounce to fire and not to repel, it's important to note that the optimal strategy for asteroids is to find a large asteroid, destroy it and all its children before tackling another one. However, we believe that bounce to repel did not support that optimal strategy, and it was hard to control the number of asteroids in the field, and players, both with perspective compensated view and without, were quickly overwhelmed by the number of asteroids. Regarding bystanders, we saw the crowd engaged with the participants, either by giving warnings such as look out or run, or cheering them up. And we did not observe any utterances in the crowd regarding perspective compensated view. That tells us, or indicates at least, that public installations might be able to use perspective compensated views without having to worry about its effects on bystanders. So to conclude, we introduce a dynamic object scale technique for floor displays called perspective compensated view. We evaluated in the wild study and in a control laboratory study. In our in the wild study, our participants had higher game scores when exposed to perspective compensated view, and in our control study, participants selected objects faster when exposed to perspective compensated views. Thank you for your time. If you have any questions, please send me an email at juliano.franz@dal.ca.